All right, good morning, chemists. We'll get started. Welcome to Chemistry 1220 with me in this accelerated course where we'll cover all of Chemistry 1220 in about 8 weeks. So this is about like time and a half speed in terms of coverage as we would in the typical fall, spring semester. So buckle up. So a little bit about me. My name is Dr. Lisa Wynn, and I will be your lecturer. So mainly I'll be interacting with you in this lecture setting. We have other teaching assistants to take care of recitation and lab, but I do communicate with those folks from time to time to make sure that those are running smoothly. But yeah, you'll be seeing me in lecture. So let's get started. Sorry, I'm kind of frazzled right now because my workflow is all messed up with not having things set up. So I am recording this lecture right now, I think, and I will be posting it under my lecture resources. So I have some intro slides to cover, and I'll just show you real quick where to find these. This is how our day-to-day operation for this course will operate. So if you go to Carmen, all right, so this is our Carmen course. How the instructional team organizes our course is mainly through modules where we separate the different components of the course. So, and we'll end with a bang at the end of class if we make it the 105 minutes. We separate the modules by course component, lecture, recitation, lab, and then I have a separate module for exam resources. So this is really how we want you to be navigating our Carmen course, is through modules. So I'll show you what's up with modules right now. So the first module is just getting started. This is where all of your kind of beginning of semester tasks live and the links for all of that. And then under there, you see lecture resources. This is where I will be posting the lecture slides, the lecture material, the videos, all of that in sequential order. So right now you see the first two lecture chapters, so chapter 13 and chapter 14, okay, posted here. So under chapter 13, I also have those intro slides. So if you have a device, go ahead and grab those. If you like to print out these slides, I have them printed two different ways. One slide per page, that's landscape, or 2 slides per page, that's a portrait type printing. I'm a 2 slide per page girl. So that's how I'll work through the slides. When we do lecture, I will go through the same exact slides along with you. So it's in your best interest to have those slides right in front of you to take notes. So grab those first day of class intro slides and chapter 13 slides on this page. And then under here is where you'll see other resources pertaining to each chapter. I have overview sheets of practice problems and very detailed worked out keys for every single chapter that you'll see here. And at the bottom, this is where the lecture videos will populate after I record and edit them. And so we'll work through these chapters sequentially. We won't finish chapter 13 this week since it's a short week, but we'll get to chapter 14 next week. I also, under this lecture resources page, have a bunch of information for you. I'm sure you've already explored the information on these slides or on these pages for you to get started in this class. I also have the syllabus gatekeeper quiz that I'd like everyone to do just to make sure that you understand the expectations of this course. So there are the lecture resources, and then there you see lab resources, recitation, and exam things. I'll be posting more once our exams get closer. So let's just go through those intro slides, back to those intro slides, and get through this rather quickly, and then we will jump right into chapter 13. All right, so 1220 summer. A little bit about me. So my name's Dr. Lisa Wynn, Nguyen, but it's pronounced Wynn, like Let's Win Chemistry. That's my YouTube handle name. play on words. But you can call me Dr. N or Dr. Wynn. That's fine. I went to graduate school here at OSU, so I got my PhD here like 4 or 5 years ago, and I've been teaching for OSU ever since. I love it here. I love teaching here. 1220 is actually my favorite course to teach. So finally, I have enough seniority. I can like choose what I want to teach, and I always request 1220. 1210. It's like baby chemistry. I like 1220 because of how applicable a lot of our concepts are to everyday life. And I'll try to embed those into the lecture material that we learn about. So a little bit about me. I was named after Lisa Simpson. My brothers named me. I live on a hobby farm with my husband and 7 chickens and ducks and 2 cats. And I like to kind of bring my life on the farm into examples in class. Not that everyone's a farmer, but everyone, you know, lives an everyday life in some type of home. And I like to bring those examples into class. So there's a little bit about me, the chickens. Here are the chickens and ducks when they were littler, but now they're bigger and they're laying. Here are all those chickens and my husband mowing the lawn, my cats in the winter in front of the fire because it's nice and cozy. And these pictures down here, I'll mention that there are 3 places, my 3 favorite places on earth. The first one is my home, my homestead, the hobby farm. I'm about to plant my transplants into the garden real soon. That's my my favorite place on earth. My second favorite place on earth is Disneyland or Disney World. I'm going in August again. Me and my husband, we're dinks. That stands for dual income, no kids. So we're like Disney adults. We're not like crazy about all the Disney stuff, but we love just the atmosphere and the eating. We like the eating. So we just go there to like eat around the world in Epcot. And that's our favorite thing. So we're going to do that in August. So that's my second favorite place on earth. And then my third favorite place on earth is Costco. I'm going to go to Costco after class or after office hours today. All right. Okay, so course logistics. So I mentioned there's different components in this class. We have 3, usually 3 105-minute lectures with me. So this goes on until like 12:15. You'll have 2 recitations a week, so Tuesday and Thursday, and you'll have 2 labs a week, Tuesday and Thursday. So you are doing chemistry nearly every single day of the week, but only for 8 weeks. So we just rip it off like a Band-Aid. All right, just get it over with. And so, yeah, you'll have a recitation and lab basically twice a week. And then you'll have 1 or 2 online homework assignments due with me that I assign about 1 or 2 a week. I chunk homework by chapter, and I'll mention details about that in a little bit. We have 4 midterm exams, and they occur in recitation. So this is scheduled class time. So hopefully there's going to be very little misses or very little conflicts because they are during recitation. They're 50 minutes. And this is very similar to how we do it in the regular school year for in recitation midterms. And it's been highly successful putting midterm exams in recitation because of the smaller class atmosphere. It's less anxiety inducing because it's just a smaller amount of people. So keep that in mind, and the schedule's down here. And then our final exam will be on the last day of lecture, which is on this calendar that you see right here. So I'll show you a little bit about this calendar. So these numbers, these are our lecture days. And then here's the schedule of events for lab and recitation. For the most part, most of the recitations occur on days that there are lab. Because I want to make sure like you're not just coming in for one component. I don't want you to just come into onto campus for just like one 55-minute recitation. So I try to keep that in mind. So there's the schedule right there. Your first recitation lab combo will be tomorrow on Thursday. So there we go. Okay, and so some common questions that I get about this course. There's only one thing you actually need to purchase for this course, and that is a lab coat. If you have a lab coat from 1210 that you took earlier, great, just keep that. But the only thing you need to purchase with the credit card is a lab coat. Everything else, the lab, I guess the lab manual, the lab access, the online homework access, the textbook, all of that was included in your course fees. So the only thing you need to purchase is a lab coat, unless you opted out of Carmen books, which actually takes a lot of work to do. You have to like fill out a form. So I doubt that any of you did that. But if you did opt out of Carmen books, then you are responsible for purchasing online homework and all that lab stuff yourself. All right, so that's the course and the schedule. All right, grading in this course. So here are the grading categories and their percentages. So you see basically everything is worth 10% of your grade. The final is worth 20% of your grade. Recitation, which we have one on Thursday, all that is attendance based. And I'll talk about that in a little bit. Online homework, this has due dates, but there's also a late penalty, late policy in place for that as well. We have those 4 in recitation exams and then our final on the last day of classes. So these are opportunities for you to earn points to get the letter grade you want. And so in this course, I don't like to say we curve the class, we don't. We publish a grading scale at the beginning of class, the beginning of the semester that is already curved. If you look at these grades, in order to earn an A in this course, you need to earn 91% of the points in the class. So you see that these grades are already curved. So the difference here between a curve and an absolute grading scale is that we've just removed that mystery of what is the curve going to be. Here's the curve right here. If you see the letter grade you want, that's what you need to earn in the total context of the course. None of the individual assignments are curved themselves because the grading scale is already curved. Yeah, and then the question here, is your final letter grade curved? Kind of. And again, it's because the grading scale we use is already curved. This is how we will assign letter grades at the end of the semester. And then the last thing, is there extra credit in this class? There is not, because it ruins the absolute grading scale if we have extra credit. So keep in mind, these are all of the grading categories, opportunities for you to earn those points to get the letter grade that you want, where we made it completely transparent what you need to earn in order to get what you want. All right, so that's grading. All right. Okay, so quick facts about lecture. I already mentioned this, showing you the Carmen page. This is where you'll get all of your lecture resources, the slides, the supplemental information, and the lecture recordings will populate at the end of each of those pages. Note that I do not take lecture attendance, and there's no points that come from lecture. So you don't need to tell me if you're going to miss a class. There are almost 80 of you. So if every single person told me every class that they were going to miss, my inbox would just be a complete mess. So you don't need to tell me if you need to miss a lecture here or there. Know where the resources are to get caught up. But in the end, it's up to you to get caught up if you are to miss a lecture here or there. But in the end, your total success in this class is dependent on how much, practice you do of those questions. Most of your points in this class come from exams. So make sure what we do in class, you can do on your own on an exam. So a lot of that comes into studying and working out these problems on your own. So there's the organization of lecture. Know where to find all of that material. Okay, great. Okay, all right, facts about recitation. I mentioned that there are, this is completely attendance-based. If you look at the schedule, there's a total of 14 meetings for recitation. There was nothing on yesterday, on Tuesday, and there'll be nothing on the very last Thursday of the semester. There's 14 different recitation meetings where 4 of them are midterm exams. So basically your attendance is mandatory there. But the other 10 recitations are just activities where you come into lecture on time, you fill out a survey to mark your attendance, and just attending and filling out that survey gives you the 10 points related to that recitation session. So recitation, if you look at the grading scale, grading categories, is worth 10% of your letter grade. In order to earn 100% in that recitation grading category, you need to attend 9 recitations. So that means everyone is granted 1 absence. all year. All right, we're at one absence. You don't have to tell me to use it. It's just automatically dropped from the grade book. But I'll also make one makeup opportunity available at the end of the year. So there's two ways you can earn a 100% in recitation, is attend 9 of the 10 recitation sessions, or attend 8 and do the makeup at the end of the year to replace one of those zeros that you got. Those are the two ways to get 100%. The majority of students every year get 100% in recitation, but keep that in mind. That's the policy I have. I do not excuse recitations. I don't give out digital alternatives. I only do for very specific students, and those are SLDS students and student athletes with documentation. Those are the students by law I'm required to accommodate, but this is the policy for everyone. Everyone gets one drop, and then there's one makeup opportunity at the end of the year. So keep that in mind. All right, and it's just attendance based. There's no quizzes or anything in it. So complete that attendance survey during recitation. It's password protected, so your TA will tell you what the password is that allows you to mark your attendance for that day. Usually I put survey questions in it to kind of get a gist of what's going on in the class. And I also include like 3 or 4 conceptual questions from what we're currently learning, but they're not graded in any way. So you don't have to like get them right. You don't even have to answer them if you don't want to, but it's a good way to gauge, are you absorbing what we're learning in class, right? But do know that they're not graded at all. How you get your points is just attending and marking your attendance for that day. Okay, great. Okay, and on midterm days, there are no recitation activities. You're just taking a midterm, so keep that in mind. That doesn't count. You can count here that there are 10 recitations, and those are the opportunities to get those points. Okay, so that's recitation. Now let's talk about online homework. So I mentioned that you already paid for this in your course fees. You don't have to pull out a credit card for this. You just have to make sure you register correctly. How many of you are coming from 12, like who just took 1210? Okay, a lot of you. Okay, great. So for the majority of you, registering for online homework is really simple. You just click on any link and you will automatically register. But for those of you, how many did not take 1210 here? Okay, a couple of you. All right, so for you 4, you'll have to grab an access code in order to register for online homework. That access code grants you access to online homework. And again, because you already paid the course fees for this course, you won't have to pay anything. You just have to grab that access code. That access code is located in the start of term tasks in a document. And you just have to make sure you go through those steps to register correctly. So for online homework, there's 1 to 2 sets per chapter that take about an hour to 2 hours to complete. I separate it by midterm. So if like a midterm occurs in the middle of a chapter, I'll split that chapter up. So it's, midterm 1 versus midterm 2 material. I set due dates for homework Monday at 10:15 a.m. So this is 15 minutes before our Monday lecture. And so how due dates operate is, let's say we finish chapter 13 today, but we're not going to, I promise. If we finish chapter 13 today, then online homework is due that following Monday, all right? If we finish chapter 13 on Friday, then that homework is due on Monday. And so I'll populate those assignment due dates in Carmen so you can see them. And I make weekly announcements of what's coming up, what's due, and whatnot. All right, so those are the due dates. You can do the questions in any order. You can do it in multiple sittings. You can just do a couple here and there. And I really encourage that because these homework sets are rather long. I'll point out that those wrong answers are penalized, so make sure you're completely understanding those concepts before submitting an answer. Hints have no penalty, so I do encourage you to use them. Not all questions have hints, but many do. So use those resources to make sure you're getting those questions correct on the first try. Each question has a limited number of attempts. Like if a question was true or false and you picked the wrong one, then you'll get a 0 on that question because it makes no sense for you to choose the other one because process of elimination, yes, that other one you didn't choose is the correct answer. So do keep that in mind that there's a limited number of attempts. Usually online homework will tell you how many attempts you have remaining. Do never request an answer for a question, because that's an automatic 0. And here's the reason. I have a late policy in place for online homework. So for any individual questions you do not submit before the due date, you can still earn partial credit for those questions that you submit late, all the way into the end of the semester. So requesting an answer gives you an automatic 0, while if you leave like 1 or 2, tough questions unanswered after the due date, just come to my office hours. I can help you and help you earn those points back to get some partial credit for those late individual questions. So here's the late policy detailed, is only individual questions are subject to this penalty if you submit questions late. And so what the policy is, it's 10% per full day late. So if you are working up until the due date and submit a couple questions like a couple minutes after the due date, the penalty is going to be so small you won't even notice it. But the further and further you get out to that due date, that's when the penalty starts to accumulate. So do keep that in mind. If you have 1 or 2 questions that you still have unanswered, and just come to me on office hours on a Monday and we talk about it and you finish it, the penalty is going to be so small you won't even notice it. So I do encourage you to eventually complete all of those assignments, even the really, really hard ones, hard questions, to maximize that online homework grade for you. All right, so for online homework, chapter 13 is probably not going to be due on Monday because we're not going to finish it, but I have an intro to mastering assignment that helps you navigate the course, and that is going to be due on Monday at right before lecture. All right, so yeah, we're probably not going to finish chapter 13, so do that intro to mastering assignment. Okay, so that was online homework. Now let's talk about lab and the tasks for lab. So again, lab access was included in your course fees unless you opted out of Carmen books. I really hope you didn't. Each lab will have a pre-lab, a notebook upload after you complete the lab in person, and then a post-lab that's due a week after you completed that lab. There are penalties applied to post labs that are submitted late, but if it means being able to finish the post lab, submitting it late is better than not submitting it at all. So here are the tasks for lab that you should be doing, since our first lab is tomorrow, is link to LabRight by clicking any LabRight link, and you'll automatically be linked to it. Again, because we have Carmen books in place, all of that was paid for already. Bring your goggles and lab coat from 1210. For the 4 of you who did not take 1210 here, that's fine. Just tell your lab TA before you go into the room that you need goggles. That you didn't take 1210 here, and they will give you a free pair of goggles, but you will still be required to purchase a lab coat, which is on the first floor of Celeste, the Chem stores, where you'll be able to buy a lab coat with a Buck ID or a credit card or something. I think it's about $20. They have sizes that you can choose from there. I really encourage you maybe to purchase that lab coat after class or well before your first lab. Don't wait 5 minutes before lab starts and think you'll get a lab coat. Give yourself plenty of time to do that. All right, a goggles, lab coat. Make sure you wear appropriate attire for that first lab. So that means, I know it's summer, but it means long pants, closed-toed shoes, hair tied back. Basically everything in red here needs to be covered on your body. And then with the lab coat on top. It's common, but we ask no synthetic leggings as well, just because the spandex and fibers in leggings aren't very protective of chemicals. So jeans are the best defense between you and chemical splashes. So keep that in mind. All right, some quizzes that the lab team would like you to complete is a safety statement quiz, a lab policies quiz, and then there's an intro to LabRight assignment or cake chemistry that is also due. I'm not sure when the due date is, but that's on the assignment itself. In order to complete cake chemistry, you'll have to use the digital version of the lab manual because you will get your physical copy of your lab manual at lab. So tomorrow, you won't get it until tomorrow. So I'll show you where to get that digital version of the lab manual in a moment. All right, so here's the lab schedule and the recitation schedule. All right, So our first lab and recitation is tomorrow. If you would like to complete cake chemistry, if you go to the lab module, all right, the second, or I guess third link here, this is your digital version of your lab manual. All right, you'll always have access to that, but you'll get your physical copy tomorrow. But this is where the digital version lives. The second link here above it, this link contains your scores and feedback for any assignments that you do. So cake chemistry has unlimited attempts. We want you to get 100% on that assignment, and it might take you multiple attempts to do that. So if you want to look back at your previous attempts, or if you want to look back at your scores of like post labs or pre-labs or something, you'll use this second link because LabRite is different from Carmen and it takes some time to sync up those grades. So the grades that you see here are where you'll see that feedback and your progress through the lab materials there. All right, what else did I want to say here? I forget. Oh, okay. Here. All right. So if you're clever, so if you remember the recitation policy, right? How do you get 100% in recitation? You go to 9 recitations or you go to 8 and do the makeup. So if you look at this schedule, there are 8 different recitation meetings on lab days, right? If you look really closely here, there's a recitation right there and a recitation right there that has no lab. I hate for you to have to come into class just for one little recitation. So if you go to every single recitation where there's also a lab day, so if you skip recitation 5 and 10, as long as you do the makeup at the end of the year, you will get 100% in recitation, or you can just attend all of them. That's fine too. So do keep that in mind. Really prioritize your attendance with recitation and lab. I know both of them occur on the same day, but I have very useful activities in recitation to help you prepare for exams. All right, so just keep that in mind. It's a little hint. Okay, midterms. All right, so those are the dates, but you can also see those midterm dates on the full schedule. They take place during recitation. If you are to miss a midterm, we do have a makeup policy where we will assign you a makeup midterm at the end of the year. The makeup policy for midterms do not come with a grade penalty. The only penalty is you have to wait until the end of the year or end of the term to take that makeup. And we don't give your responses back if you take a makeup. So do prioritize taking those midterms during recitation. We have this makeup policy in place because I want to make sure I get exams back to everybody in a timely manner. So I will try to get those your grades and your responses from midterms back as soon as possible. And so that's why we have that makeup policy in place. If you are to miss one, we're just going to push it to the end of the year for you to take at the end of the year. So do know that making up a midterm, there's no grade penalty, but you're only allowed one. You're only allowed one. After one, if you miss 2 or 3 midterms, yikes. But then we'll need documentation at that point. All right, I'll mention if you are an SLDS student and you take exams with SLDS, it's your responsibility to schedule those exams yourself with SLDS, but we will put together the assignments to make sure you get those accommodations you need. I'll send out individual emails to students who do test with SLDS, but mainly this talk is for the majority of students. Okay, midterms, they are administered via a Carmen quiz, and I'll publish multiple practice exams for you to see what the exams will actually look like. So that means it's all a Carmen quiz. So it's like multiple choice, pull down menu, numerical response. You don't have to show work. Essentially, since it is pre-graded as a Carmen quiz. And again, I'll show examples here in the coming weeks when our first midterm comes up. You will get a supplemental information sheet that has equations, and it'll serve as scratch paper, and you'll be given a periodic table, and I'll post these materials well before that first midterm so you can see exactly what you'll get at that midterm exam. And then finally, I will post practice exams for your preparations for these 4 different midterms. Our final exam is cumulative, and it occurs on the last day of classes, so Friday in lecture. So it is cumulative, and I'll make sure to make clear what material will be assessed on midterms and the final as we go through that lecture material. Okay, midterms. All right, calculator policy. These are the only permitted calculators on exams. All of these are Texas Instrument calculators. So the TI 83, 84 series, it can have a plus or a CE in the name, that's fine, but we do not allow the TI Inspire. The reason we don't allow this one is because of that keyboard. If you have a Casio calculator, technically that's not allowed either for our calculator policy. So do keep that in mind. These are the only ones that we allow. I will point out that Lockdown Browser does have an onboard calculator in it as well. It just really sucks to use. Like, it's not nice to use. But if you're in a pinch, that calculator is always there for you as well. We have about 2 or 3 weeks before our first midterm, so do make sure that you have one of these calculators for that exam. But I do encourage you to use the same calculator on online homework and your studies so you're familiar with where those buttons are on the calculator. Okay, great. All right, so tasks for lecture. Make sure you register for online homework. I'll show you how to do that in a couple slides here. Get 100% on the academic misconduct quiz. We have the due date set for Sunday. This is our participation roster. So if you don't do this quiz, you might be dropped from the class, right? So I'll send angry emails to students who don't do that. Get a 100% on the lab quizzes and all of that, and get 100% on my syllabus gatekeeper quiz to make sure that you are understanding the expectations of this course. And then finally, explore our Carmen page because there's tons of resources there for you. Any questions that you may have are probably answered somewhere in our Carmen page. That intro assignment will be due for online homework will be due on Monday, our typical online homework due date. All right, those are the tasks for lecture. Okay, all right, so how to reach me. I will have office hours directly after class on Monday and Wednesday. So that includes today. So if you just follow me to my office, we can chat a little bit longer about chemistry or any questions that you may have. So it's directly after lecture in my office, which is Evans 1043. But if you just follow me to my office, I'll show you where it is. Or if you need to meet with me outside of these times, you can feel free to email me and set up an appointment for that to happen. If you have any questions, email me directly at win.1342@osu.edu. Do not use Carmen messaging to email anybody in the chemistry team. Most of us, I would say the majority of us, prefer direct emails because they're a lot easier to navigate and they're a lot easier. We get a lot of emails. So we would like these emails sent to us directly and not using Carmen messaging. But I'll point out, if you have a logistics question about this course, check out my facts page that is on our lecture resources. It just says Dr. N's facts page. And I have a compilation of a ton of questions that I've gotten over the years about this course getting started. So do check that out. I imagine 99% of the questions you may have is probably on that page. So again, I'm the lecturer, point of contact, but our teaching assistants are also valuable resources, and you'll meet them tomorrow. Outside of class, we have a tutor center in Celeste, so the building over here. They have specific hours, and you can see those hours here at this link. Things pertaining to lab should probably be either sent to your lab TA or your lab supervisor. So if you contact me something about lab, I'll probably just push you over to them unless I know the answer. But that's their email right there. They can help you with lab things. Okay, so that's how to reach me. And then finally, here is a page that summarizes all of the policies if you are to miss class, because I got a ton of these questions earlier in the year before the semester even started, like, yes, like folks are going on vacation or whatever. I know it's the summer, people want to go on vacation. So here's the full schedule of events. I will point out that on May 24th, I've canceled lecture on this day. Right, for all of our benefits, about halfway through the semester, but there's no lecture on this day, so we can have a nice long Memorial Day break kind of in the middle of the semester. So that's nice for everyone. But if you are to miss a chunk of time in this course, this is how you can make it up. We have some embedded opportunities for you to earn back points if you are to miss, but outside of what we give to everyone, if you are to miss class, it will probably start to negatively affect your grade. So these are the opportunities we give all students if they are to miss a recitation or lab here or there. So again, for lecture, if you have to miss lecture, you don't have to tell me. Know where all of the materials and the lecture recordings are. If you miss recitation, know that everyone gets one free drop and there's a makeup opportunity at the end of the year. For midterms, there is already a makeup midterm policy in place. You just have to request it using the request form. For lab, if you have to miss a lab, email the lab supervisors within 1 week of that absence, but as soon as possible is preferable. And so the rules for lab are your first missed lab, we will give you a penalty-free makeup lab, depending on what lab you miss. So contact them about how you'll make that up. But yeah, everyone gets one free miss, and we replace that missed lab with a digital alternative to a different lab. And then your second miss, if you are to miss 2 labs, we'll give you an alternative, but this does require documentation to waive a penalty. So everyone gets one free makeup, but the second one does come with a penalty if you don't have proper documentation. And then finally, for the final, if you are to miss the final, since this occurs during class, there are penalties applied if you are to delay the final exam. So that is the full policy there. I would print this out, hang it, and constantly refer to it if you are to miss class. Those are the policies for all of the course components. All right. So for the 4 of you who did not take 1210 here are the steps for mastering chemistry, or all the steps to register for online homework. For the majority of you who are coming from 1210, if you click on any homework link, you'll register automatically. Your access code from 1210 will just follow you, all right? But for those of you who haven't used the access code before, this is where you get the access code. It's right here. If you go to the start of term tasks, there's a document. It's called Register for Online Homework. In this PDF, you will find a 6-word access code. I think one of the words is like Hobbs or something, or Holmes or something like that. So keep that access code nearby, you'll need it. Then to register, you'll click on Access Pearson in our Carmen course. You will agree to some stuff. You'll sign in or make a new account. I'll point out that your email that you use for Pearson, it doesn't have to be an OSU email. It could be any email if you already have one. So you can create a new account or sign in. If you did not take 1210 here, to register, when you get to this page, you want to select access code. Since we gave you an access code, do not pay, do not pay, do not say, I want a free trial. Don't do that. You have the access code, use the access code. And then you'll just input the access code and then you're done. Even if you're like waiting for financial aid, it doesn't matter. Just use the access code, right? And then you'll be fine. All right, so that is online homework. All right, if you get a page that asks for a course ID, don't do that. Go through these steps and do the access code. And that's how you register for online homework. All right, so any questions about this course before we get started? Any questions? Because we're just going to jump right into chapter 13. Yeah? All right, so let's jump into chapter 13. And then once we make it to the end, we'll end with a bang. End with a bang. Okay, so let's go grab those chapter 13 slides. So go to the lecture module to grab them, and we will move on to chapter 13, properties of solutions. So I'll mention here, so for those of you who did not take 1210 here, or it's been a while since you've taken chemistry, I'll point out the concepts that I'm assuming that most of you know from Chemistry 1. So in this chapter, chapter 13, we're going to build on the concepts we already know about intermolecular forces. So that means knowing Lewis structures, molecule polarity is a very important concept in this chapter. Because in Chemistry 1, we looked at intermolecular forces present in pure substances. So if, let's say I had a sample of pure water, Water is H2O. It's a polar molecule. So it has a pure sample of water, has London dispersion present. It has dipole-dipole attractions. And most importantly, it has hydrogen bonding. And so those attractions between the particles cause for a lot of chemical properties and physical properties that we see in water. It has a really high boiling point. And so all of those factors, those intermolecular forces, affect what we actually see and observe about these samples. So we're going to expand on that in chapter 13. And instead of just thinking about pure samples of water or methane or whatever, ethanol, we're going to start making mixtures. So a mixture is something that has two different components in it. And so what we're going to be doing is mixing these intermolecular forces and looking at the energetics associated with that. So from Chem 1210 or Chemistry 1, do review intermolecular forces, and we'll talk about that a little bit here. All right, so let's recap from 1210 or Chemistry 1, the difference between a pure substance and a mixture. So a pure substance is a substance that has distinct properties and composition. But my tip to identify something as a pure substance is that you can write one formula to describe it. So if we had a sample of pure water, H2O, H2O is one formula. So it's one pure substance because you can write one formula. But you know, if we had something like this piece of paper, right? It's made up of a lot of different things. Can you write one chemical formula to represent what this is? No, it's made of a bunch of things. So that's why we can't say this is a pure substance, because I can't just write one formula for it. If I had a pure hunk of gold, gold is just Au on the periodic table. So that hunk of gold would be a pure substance. So now to come off of pure substances, we can mix these pure substances to form mixtures. So a mixture is a sample that contains two or more pure substances that are not chemically combined. But my tip here is you have to, if you wanted to describe a mixture, you're going to write more than one formula in order to represent that. So let me give you a example: salt water. What is salt water made out of? Salt and water. Yeah, I don't want you to think about it too much. So does salt have a chemical formula? Yeah, NaCl. Water, does that have a chemical formula? Yes, H2O. So here, salt water contains two different formulas: salt, NaCl, and H2O, but they're not chemically combined. We just mix them into a homogeneous mixture. So salt water would be an example of a mixture because we have two different formulas to describe it. For the most part in this chapter, we're going to talk about homogeneous mixtures. So things where we mix them and it creates one single phase without distinct differences. So uniform properties and compositions throughout. So these homogeneous mixtures, we can also refer to them as solutions. So solution and homogeneous mixture, they're synonyms of one another, but they actually occur in all phases of matter: solids, liquids, and gases. But for some reason, when we think of the word solution, our mind automatically goes to liquid. But anything, the air that we breathe, made up of a lot of different things: oxygen gas, CO2, nitrogen. That's also a mixture. It's also a homogeneous mixture. Therefore, the air that we're breathing is also a solution as well, even though it's in the gas phase, because it still follows the properties of a homogeneous mixture. All right. Okay, so those are our review tips. Okay. All right, so let's think about solutions. Remember, solution just means homogeneous mixture. That's all it means, right? So we have to have more than one pure substance present when we make a solution, when we make a homogeneous mixture. For the most part in this chapter, we're going to talk about liquid phase solutions, but gases can also form solutions as well. So the components of a solution include the solute and the solvent. Just think of salt water. How do you make salt water? You take a beaker of water and you throw salts in it and you mix it up. So in a solution, we have two different components: a solute and a solvent. The solvent is the thing that's usually present in the larger quantity. So for 98% of our examples, water is going to be our solvent. but there are other solvents out there too that we can dissolve stuff in. But for the most part, we're thinking about water as our solvent because water is all around us in our world. So here again is my salt water example, salt water. This is the #1 example of a homogeneous mixture, a solution, salt water, where NaCl is our solute and water is our solvent. All right, water is the more abundant substance present in this mixture, and we add just a little bit of salt to make that salt water. And so what you see here, salt water, if you look at a sample of salt water and compare it to a sample of pure water, just by looking at it, can you tell the difference? No, they both basically look the same because they're both homogeneous mixtures. So keep that in mind. We're going to be looking at different properties. How does salt water differ from pure water? Some things that we talked about in Chem 1210 about samples of solutions. We talked about, we can talk about the concentration of that salt. All right, so in Chem 1210, if I gave you a saltwater sample, you may be able to calculate the concentration in molarity for that salt. We could ask you about the conductivity of that sample. Salt is an ionic compound, so it fully dissociates in solution, releasing those ions. So salt water does conduct electricity. In 1210, we talked about dissolving stuff in water and determining, is it a soluble or insoluble salt? So those were our solubility rules. We talked about that in 1210. We'll expand on that in this chapter. And then finally, in 1210, you talked about enthalpy of dissolution. So this was coffee cup calorimetry. For some of those salts that you dissolved in water, sometimes the water heated up, sometimes it cooled down. And so we'll look at those details in this chapter as well. New topics that expand on these previous topics that we'll talk about in this course is looking at different concentration units. So it's not just molarity. We'll talk about other concentration units, molality, mass percentage, mole fraction, those different concentration units. We will look at different properties of solutions. So like a saltwater solution actually has a different freezing point and boiling point temperature than pure water. And so we'll look into that. We'll look at saturated and unsaturated solutions. So the question is, well, how much salt can we dissolve into a solution before no more salt will dissolve? We'll look into that. We'll look at vapor pressure of solvents, and then we'll talk about pH later in chapter 16. So we're going to go into a crazy amount of detail of solutions. That's basically the next, 5 weeks of this course. We'll be looking at solutions, usually done in water. All right. So let's think about how we make a solution. So when we make solutions, when we mix things together, there's two thermodynamic forces in play. There's two different components. There's an enthalpy or energy component, and then there's an entropy component to making mixtures. So for now, I'm going to use entropy as like this magic wand to explain weird phenomena that we see. But in chapter 19, I'll explain more about what entropy is and the details of entropy. But for now, I'm just going to use entropy as this magic wand to explain things that seem unexplainable at the time. All right, so let's think about this example. Okay, we have two gases separated by a barrier, right? So we have pure oxygen over here, pure argon over here. So these two samples are pure substances on their own. Well, what will happen, we think, if we remove this barrier between them? If both of these are gases, so let's say oxygen and argon, our mind finishes the picture how? That these particles, since they're gases, they're all bouncing around, and without us doing anything other than just removing this barrier, this is what happens, that a mixture is formed, that the argon particles and the oxygen molecules, they disperse themselves evenly throughout this container. So this process happens spontaneously. Once you remove that barrier, those two things will mix with one another. If you put a drop of food dye in a beaker of pure water, eventually all of that dye will mix into that water, creating a uniform mixture. All of this happens spontaneously. So what is a spontaneous process? It's a process that happens without energy input from us. All we did was just remove this barrier, and these particles mix themselves. When you put that drop of food dye into water, over time, all of that dye will mix on its own spontaneously, given enough time. Yes, we can make it go faster if we mix it up with like a spoon or something, but mixing happens on its own without energy input. This is a spontaneous process. So the reason this happens is because of entropy, right? That the spontaneous mixing of gases occurs due to an increase of entropy in this overall process. Energy is actually not very much involved in this process because no bonds are being made or broken. So here, there's, again, two different factors in how mixtures are created. There's an entropy component and an enthalpy, an energy component. But in this example, enthalpy is not very important because there are no bonds being broken. No bonds are made or broken. So delta H is basically 0 for this reaction, right? That no heat is actually generated because no bonds are being made or formed. But a change is happening because a mixture is being formed. So what's really important here in creating mixtures from gases where no bonds are being broken or formed is that entropy is the reason that these things are mixing. All right, so there's kind of a entropy example of the solution process. So let's look at the enthalpy component of solution processes. Okay, so the two examples that I will use and relate to our everyday life is there's two types of things that might be in your first aid kit. You might have a hot pack and you might have a cold pack in your first aid kit. A hot pack works, you like break a little vial inside the hot pack and it generates a lot of heat and you put it on like whatever sore spot you have on your body. Versus a cold pack, you break the little tube inside of it and the pack gets really cold and you put it on whatever sore spot you have. So those two objects in your first aid kit are highlighting the enthalpy changes in these chemical reactions. So when you use a hot pack or a cold pack, when you break that little tube inside of one of those packs, really what you're doing is releasing water or releasing salts in that cold pack. And basically you're just making a mixture, you're making a solution. You're just doing a chemical reaction and dissolving a salt. So in the first example, we're gonna look at the hot pack example. So heat is generated when we break that little vial in the inside. So in a hot pack, it obviously feels hot in that hot pack. So when we think about what is the sign of delta H for this reaction, turning, so in a hot pack, it's made with calcium chloride and you're just breaking a little vial of water and making a calcium chloride aqueous solution. Delta H for this reaction, for an exothermic reaction, a reaction that generates heat, is what sign? It's a negative sign. Yes, it is a negative sign. All right, so this is an important concept from 1210 and kind of the basics of thermochemistry is when a reaction releases heat. I know that we feel it get warm, but in the grand scheme of things, as chemists, we care about the reaction, right? And what we're observing doesn't really matter. Yes, like we're getting warmer, but we're getting warmer because the reaction is releasing energy. So it's losing that energy, it's releasing heat. So the delta H of a reaction for one that's hot or exothermic is a negative sign. And that's a very important concept that students often flip because they see, oh, it gets hot, delta H must be positive. No, it's not. It's because the reaction released heat, we feel that heat coming off. So do recognize that that's the reaction releasing the heat. I always tell students, stop being selfish, right? Stop being selfish. Yes, you are feeling heat come off, but it's because the reaction lost it. You don't matter, it's the reaction that matters. All right, so let's look at the details of what's actually happening in an exothermic dissolution process. So when we dissolve a salt, heat is released. Let's think about it kind of step by step. What happens? So we can think about theoretically what happens when we make a saltwater solution, right? We have salt and we have water. And then when we mix it together, now we have salt water. So if we think about the separate steps that happen, what's happening here is that intermolecular forces that are at play, because we're not making any new bonds. We're making new attractions, new intermolecular forces are at play. So when we make a solution, you can think, okay, what if I break all of those solvent particles? Let's take all of those water molecules in the sample and break them apart and spread them out. That takes an amount of energy. So this process has a positive sign. Let's do a different color, green, has a positive sign of energy. It takes energy to break apart all of those solvent particles, right? So we're breaking apart the water. We can do the same thing to the solute particles. Let's take all of the solute particles and break them up as well into the gas phase. So you see here's another upward arrow. All right, delta H of solute, the energy it takes to break all of those solute particles also requires energy. So these two arrows, let's add them up and then make this new arrow. This is the sum of breaking apart all the solute particles and solvent particles, all right? So now we have all of these solute and solvent particles just floating in the air in the gas phase. That never happens. This is just kind of a theoretical example. And now let's bring them back together, right? So when we bring particles back together, attractions now take over. And so this is what we call the enthalpy of mixing. When we mix our solute and our solvent particles together, we get this new attraction term right here, delta H of mixing, right? So this downward arrow, this is the attractions between your solute and your solvent. So in this example, delta H of mixing is a very negative value, meaning that your solute and your solvent are highly attracted to one another. Because look at where we end up. After all of this process is done, we break apart all the solvent, we break apart all of the solute, and then we bring them back together. Our final resting place is lower in energy than where we started. So this is why delta H of our reaction is an overall negative sign. This is an exothermic process where we end up is lower than where we started. We started with pure salt and pure water, but then we mixed them together. The attractions between the solute and the solvent now are at a lower energy place, and this releases energy, all right? So we can add up all of these steps using Hess's law. And so I'll point out that delta H of solution, this is what we observe. All right, so in this example, this is an exothermic process. We would observe heat is released in this process. The reason heat is released in this process is because delta H of mixing is a very large negative number. All right, delta H of solute and solvent are smaller positive numbers, but in the mixture, we have lots of attractions between the salt and the water that the overall process is a negative sign. So when we think about, calorimetry and thermodynamics in a hot pack in an exothermic reaction, the bonds and the products are stronger, right? Because in this example, there's high attractions. There's high attractions between your solute and your solvent. All right, and so this is why for some salts, when we dissolve them in water, they're exothermic overall. It's because the bonds that we create in the mixture, in the saltwater mixture, are a lot stronger than what we started with, right? And so it's important to note here is that this energy change, enthalpy, is the reason that this solution is created in the first place. The reason that this is a spontaneous process is because enthalpy is driving this reaction forward. It's very exothermic, so it's very spontaneous in that forward direction. So we can say here that exothermic dissolution processes are driven by enthalpy. Any salt that you dissolve and heat is released is driven by enthalpy. And that's basically how hot packs work. That once you break that, water packet inside the hot pack, the reaction moves forward on its own because it's driven by enthalpy. That reaction's giving off energy on its own. All right, so that's a hot pack. So now let's talk about a cold pack. This one's a little bit different on how it works, but we're going to use the same exact graph. It just looks a little bit different. So in a cold pack, these feel cold, right? They're cold because delta H of this reaction, delta H of the reaction is a positive value. This is an endothermic reaction, right? And it's weird because it gets cold. For some reason, when we think of cold, we think of negative signs. But in this example, delta H of the reaction is positive because when we hold the reaction and we feel it get cold, the reaction is gaining heat, gaining energy. Where's that energy coming from? It's coming from you. And that's why you feel cold, because the reaction is literally stealing energy, stealing heat from you. And so endothermic processes that feel cold are have positive delta H of reaction signs. You will mess this up, right? So just remind yourself that you don't matter, the reaction matters. And hopefully you'll get the sign right over time. All right, so the compound that we dissolve that's present in a cold pack, so we're still dissolving a salt, it's just the identity is different. So in this example, the dissolution of ammonium nitrate is an endothermic process. So let's think about how this salt dissolves. We're gonna think about those same 3 steps. We're gonna break apart our solute, we're gonna break apart our solvent, and we're gonna bring them back together, but a little bit differently here. So same exact steps. This first step is we're just breaking all of our solvent particles. We're ripping all the water molecules, breaking all the intermolecular forces between the water particles. Then we're going to do the same thing to the salt. Let's break apart all of the salt particles, the solute particles, throw them up in the air, break all those intermolecular forces, and then we're going to bring them back together. And that's what this last step is, delta H of mixing. Again, this is the same delta H of mixing. This is the attractions between your solute and your solvent. But in this example, if you compare this to the previous slide, this delta H of mixing, it's still a downward arrow, but let's compare it to the previous step. In exothermic example, delta H of mixing is a very large negative value, right? And the reason is because the attractions are strong. But in this example, are our attractions very strong? Nope, they're a lot weaker because the arrow is a lot smaller here. So in an endothermic dissolution process, the attractions between your solute and your solvent are very weak. These are very weak attractions compared to an exothermic process. And then the consequence of that, if you look, the overall process for this reaction, see, now we end up at a higher energy place than where we started. So in this example, delta H of our overall reaction is actually a positive sign. And this is why we call this process endothermic, because the attractions in the mixture are weaker than the attractions between the pure solute and the pure solvent on their own. All right. So in this example, in a cold pack, the reactants actually have stronger bonds. All right. That we have weak, I guess, solute, solvent attractions. So in this example, when the reaction moves forward, we're actually making weaker bonds. So you might be thinking, well, then why does this reaction happen overall? How does this reaction on its own go uphill? How does it go up in energy uphill? And this is an example where I'm just going to use entropy to explain something, where endothermic dissolution processes, these are driven by entropy, right? These reactions still do happen on their own, but something else is pulling that reaction along. Entropy is actually pulling it along. So here, we're going to say delta S is a large positive sign, but we're going to talk about this later in chapter 19. But what we see here is that endothermic processes are driven by entropy, where exothermic dissolution processes are driven by enthalpy. but both of them are spontaneous on their own in these examples. A cold pack works, a hot pack works, but the thermodynamics behind why they happen on their own slightly differ. All right, so in both of these examples, these arrows, and using Hess's law, operate off of this, this equation, where the delta H of our solution, this is what we observe. This is whether we say, oh, is it endo or is it exothermic? Is the reaction endo or exothermic? Are related to these three steps we talked about. The energy to break apart all of the solute particles, you know, that's going to be a positive sign. The energy to break apart all of the solvent particles, also going to be a positive sign. But delta H of mixing is an attraction term, so it's a negative sign. So this is attractions. Attractions. All right. Okay, so those are our hot pack, our cold pack. So let's just review all of those signs and then do some math using this equation. So remember, the signs of delta H for all of these steps of this process, do remember positive delta H values means that these processes require energy, while negative delta H signs release energy. And so when we think about these steps, we're either breaking bonds or we're making bonds, or we're breaking intermolecular forces or bringing attracted particles together. So do know, understand the signs there, because it can get quite tricky, where endothermic processes require energy. This is usually due to repulsions, while exothermic, these release energy, and it's due to bringing attracted particles together. So if we review the signs here for an exothermic versus an endothermic dissolution process. So we're just reviewing what we just did. So we're dissolving different salts. Some of them have a exothermic process, some of them an endothermic process. We talked about different delta H's here, but all of these delta H's refer to different things. Delta H of solution is what we observe. This is like what you would measure in coffee cup calorimetry. In an exothermic dissolution process, delta H of your solution is what sign? It's going to be negative. While in an endothermic dissolution process, delta H of your solution is going to be a positive sign. All right. So if you did coffee cup calorimetry with a reaction that has a negative sign for delta H of solution, how will the temperature of your water change? Will it go up or will it go down? For an exothermic process, yeah, it goes up. You don't have to raise your hand. You can just yell it out. We're very informal in this space. Yeah, so your temperature is going to go up. It's going to heat up. Versus in an endothermic process, if you put this junk in water and you mix it up, which way will the temperature of that water go? It's going to go down. Yes, it's going to go down. And that's weird, right? Temperature goes up, but delta H is negative. That's weird, but it's because water is your surroundings. The water is like us. It's gaining that heat that the reaction released. In an endothermic process, the water is losing heat. So the temperatures go down because the reaction is taking the heat from its surroundings. It's taking heat from that water. So the temperature goes down. So that's what we would observe, right? So for these two processes, delta H of the solute, so the energy to rip apart all of the solute particles, are also going to be positive signs, because it takes energy to rip apart, to break chemical bonds or to break intermolecular forces. Solvent particles are also going to have positive signs here, because it takes energy to rip apart those solute particles. But what's different is delta H of mixing. Remember, this is an attractions term, right? An attractions term. So we're making new bonds. We're bringing attracted things together. So delta H of mixing is always going to be a negative sign in these examples, delta H of mixing. But the difference is, in order to get a negative sign of delta H of solution for an exothermic process, delta H of mixing is very large and negative. And this is because there are strong attractions. There's a strong attractions between your solute and solvent. versus in an endothermic process, it only had a small, short little delta H of mixing arrow. So delta H of mixing for an endothermic process is still negative, but it's weak attractions. Weak attractions. All right, so that's the big difference there of all of those signs. All right. And the big difference in how we observe it in our natural world is due to the attractions between strong mixing versus weak attractions in our endothermic process. That's why we see differences in delta H of solution for these different examples. All right. So all of these signs is just the conceptualizing this equation that we're going to use in the next examples. If you know how much energy it costs you to break apart your solute and your solvent, and you know your delta H of solution, you can estimate, okay, how much attractions is present in your mixture. So let's just do a couple of examples. The math is more straightforward, but the concepts are the hard part, and typically what we test on here, because these calculations are rather easy. It's just, can you assign the correct things to the correct variable inside this equation? So a lot of this is just reading comprehension. All right, so this first one, I tell you the heat of the solution for dissolving a substance in water is negative 11.5 kilojoules per mole, right? So this process is exothermic. If you throw this salt into water, it's going to heat up the water because it's exothermic. So here I give you delta H of solution. And I tell you the heat required to separate solute particles is 148 kilojoules per mole. So I give you delta H of solute. And I tell you the heat required to separate solvent particles is 210 kilojoules per mole. So I give you 3 of the 4 variables, and here we are calculating delta H of mixing. So it's all just reading comprehension. Can you assign the correct things in the correct place? And so it's just solving for that missing piece. So putting it together, negative 11.5 kilojoules per mole equals the energy to break apart all of the solute particles, so 148. All of these are in kilojoules per mole, plus the energy to rip apart all those solvent particles, so 210. And we're going to add the delta H of mixing, and this term is what we are solving for. So remember that delta H of mixing should come out to be a negative number because delta H of mixing is an attractions term. And I have the answer in the corner there. Delta H of mixing, if you solve for this, must be negative something, 369.5 kilojoules per mole. So it's just some math. And it does make sense that that delta H of mixing is a negative sign because mixing is an attractions term, while these two terms are positive because we're breaking the bonds or breaking the intermolecular forces between those substances. All right. And this next one, okay, so for a particular ionic solid, I tell you delta H of solution is 15. I'm just going to drop the units. All of this is in kilojoules per mole. So I tell you that delta H of solution is 15. I tell you that the enthalpy to break apart all the solvent particles is 210. And here I tell you the enthalpy of mixing is negative 734 kilojoules per mole. So in this case, we are given everything except the enthalpy to break apart those solute particles. So that is what we are solving for here, delta H of solute. All right, all of those units are the same, so I just dropped the units. And so here we are just solving for that missing piece. It's different here. We're just solving for the enthalpy of the solute. And so I have the answer right there. Delta H of your solute, you solve for that mathematically, is something like 539 kilojoules per mole. There we go. And so again, these questions a little bit more straightforward. Just make sure that you are using this equation and assigning the correct quantity to the correct variable inside that equation. Remember, delta H of solution is what you would observe if you did coffee cup calorimetry, right? So in this first example, this exothermic reaction would heat up water. But in this example, this ionic solid, if you threw the second example into water, which way, how will the temperature of the water change? It's going to go down. Yes, because this is an endothermic process. This one is endo. Perfect. Okay. So there we go. So that's the math of mixing stuff. So we'll talk about the, we're going to talk about saturated solutions. And then we'll talk about the intermolecular forces that are responsible for the magnitudes of attractions and repulsions. Okay, so saturated solutions. So I don't know about you. Do you remember this graph or this table? No? Okay, well, this is how we use this table. If I give you a salt, so like NaCl, or like calcium chloride, or ammonium nitrate, or something like that, you could use this table and predict, will it dissolve in water or not? This was particularly useful for predicting double displacement reactions. You mix two saltwater solutions together, sometimes a reaction happens where a solid is produced. So when a solid is produced, it means that one of those compounds is insoluble in water. So when we did double displacement reactions, compounds that were soluble, we gave the aqueous designation in our net ionic equation, or when they were insoluble, we said that they were solids, right? So like lead iodide, for example, is a compound that's mostly insoluble in water, so we said it was a solid, right? But in Chem 1210, we were always working with very dilute solutions. So you might be thinking, well, okay, yes, you can dissolve salt in water, it becomes aqueous, you get this homogeneous mixture. Or you dissolve calcium chloride in water, you get this homogeneous mixture. But at a certain point, you keep adding salt to water, there has to be a certain point where no more salt will dissolve in the water. And that's what we're talking about here. We're pushing the limits of making solutions. And this limit is called a saturated solution, all right? So yeah, let's just think about it, okay? Add a little bit of salt and water. Okay, here's pure water, here's salt. It dissolves. The ions separate. This solution would conduct electricity because there's anions and cations floating around freely, right? What if we add even more salt? Okay, if we add even more salt, look, we just, separate more ions. So we see that this solution will conduct even more electricity because there's more ions present. But what if we keep adding salt? You keep adding salt, at a certain point, no more salt will dissolve in that water. If you can think about this kind of in the kitchen. I feel like with saturated solutions, this oftentimes happens in the kitchen. Maybe you're dissolving like protein powder in milk or something, and you add way too much, and you mix it, and that last bit of solid never actually goes into the solution. And so when you're drinking your protein shake, it's all chunky at the bottom because not all of it dissolves. So that, again, is an example of a saturated solution. There's a certain point where you add way too much solid and no more will actually go into solution. So we can use graphs to help us determine, okay, where is the limit of your saturated solution, or how can we change the solubility of a saturated solution? All right. So in this picture, on this slide, there's only two pictures that actually depict saturated solutions, and it's these two. These two are saturated solutions, meaning that there's this hunk of solid at the bottom that can't dissolve into the water. It's like having your chunky protein shake because you added way too much, like you ran out of milk, so you only have half the liquid present, and there's chunks at the bottom, right? So let's think about this. Let's just use our intuition for a second. If we had a saturated solution like this, like we had so we had water, we had salt, but there's like chunks of solid at the bottom. There are two ways we can get that solid to dissolve. Can someone just think of one way? Like, think you're in the kitchen. You're in the kitchen and you want to dissolve a hunk of solid stuck at the bottom of your measuring cup. How can you get that solid to dissolve? There's two ways. Heat. Yeah, heat it up. Heating up is one way you can get that solid to dissolve. So that actually changes the solubility, the point at where saturation occurs. There's also another way you can dissolve solid. Add more water. Yes, adding more water also does it. Very good. And so we'll talk about both of those examples and how they relate to saturated solutions. Okay, so let's just quick get a definition of a saturated solution out of the way. So a saturated solution is a solution where you have undissolved solute in contact with solution. So here's an example, all right, or the examples that we had up here where you had the solid, but you also had like very highly concentrated stuff around it. These are examples of saturated solutions. If you look at these different examples, these ones can still accept a little bit more solid, so they're not saturated. But here in these examples, if you were to add more solid to these two beakers, that solid's just going to sink to the bottom. It's not actually going to go into solution. And so these two depict saturated solutions. So our definition here is a saturated solution is in contact with undissolved solid at the bottom of your beaker. And so you can think about a saturated solution will have your solute and solution present at the same time. All right, the highly concentrated aqueous thing and the solute also sunk at the bottom. Where a saturated solution will not accept any more solid to be dissolved, right? And so this process of creating a saturated solution is actually a dynamic equilibrium, which we'll talk about in a lot of detail in the coming weeks. We have this double-sided arrow here that we'll talk about, or this equilibrium arrow we'll talk about in later weeks. But this process goes back and forth when we have a saturated solution. Okay, so saturated solution, great, okay. Okay, so let's talk about saturated solutions and measuring its concentration via its solubility. So here's a graph of the solubility of sodium acetate, so some salts, but here at different temperatures, right? So how we read this graph is that we see that solubility is temperature dependent. So how we read this graph is on the y-axis, we have how much of your substance will dissolve in 100 grams of water. And then on the x-axis, we have temperature. So I mentioned that solubility is temperature dependent. You all were very smart and knew that, okay, to dissolve that last bit of like sugar at the bottom of your whatever, sometimes you can just heat it up to get it to dissolve, or you can add more water. So doing so navigates us in different portions of this graph. So what we see in this graph is this portion of our graph. If you have a solution and if you make it at 25 degrees Celsius, all right, if you put 50 grams of sodium acetate in 100 grams of water at 25 degrees Celsius, it is unsaturated, meaning if you take this solution and add more solid, it will dissolve. But when you dissolve that solid, the concentration starts to go up. Okay, so then let's add 10 more grams of sodium acetate. Okay, if you keep adding and adding and adding sodium acetate, then you'll hit at the same temperature, you'll hit this saturated line. So this saturated line is the limit in which you can dissolve that amount of solid in 100 grams of water, right? So once you're saturated, any more added solid is just going to sink to the bottom of that container. It's going to sink to the bottom of the container, and it's not going to actually change the concentration of the liquid around that solid. But what we see here is this region is called supersaturated, meaning if for some reason you are able to make a solution that holds more than it's actually able to, it's supersaturated. This is very unstable, and it's actually very hard to make a supersaturated solution. For the most part in lab, you are going to be working with unsaturated solutions. Those are like the things that you grab from the stock cart with concentrations written on them. Those are unsaturated solutions. While a saturated solution is where you've dissolved so much stuff, you're at the limit at how much that water can hold. All right. So let's see if we can't just navigate this graph really quickly here. Okay, so what is the solubility of sodium acetate at 30 degrees Celsius? So let's read the graph. Let's go to 30 degrees Celsius. I think that's right here. That's right here. So the solubility of sodium acetate is going to sit right on that saturated line. So it's going to be right here at whatever this gram per 100 grams of water is. So I think that's one tick below 100. So to me, that looks like 90. So that means the maximum solubility of sodium acetate, you have the ability to dissolve 90 grams of solid in 100 grams of water. That is the limit of how much sodium acetate you can dissolve, given this graph, right? At 30 degrees Celsius. Okay, so based upon that, what kinds of solutions are these? Let's say, are they unsaturated, supersaturated, or saturated? Okay, so if we put 50 grams of solid and we dissolve it in 100 grams of water at 30 degrees Celsius. So if you look at this graph, you see that, oh yeah, 50 grams and 100 grams of water is way well in that unsaturated region. So this would be unsaturated, right? Because we've only added 50, but we're able to add 90. So this solution, this unsaturated solution, has the ability to accept and dissolve more solid. All right, what if we put 100 grams of solid and we mix it in 100 grams of water? We mix it as much as our heart can take, but we see that we aren't able to dissolve all of it and there's solid sunk at the bottom. What kind of solution is this? This one is what? It is saturated. Yes, it is saturated because it cannot hold any more solid. Is all that 100 grams dissolved in the 100 grams of water? No, because I told you that there's solid sunk at the bottom. Do you know about how much solid will be sunk at the bottom? About 10, yeah, because again, the saturated, only 90 of it will be in solution, while 10 of it is going to be as a solid at the bottom. Okay, my handwriting's really bad. At the bottom. I will point out that right now I have to record on Zoom. It's not always going to look like this. It'll look better. I need to set up my hardware recording so it'll record automatically. So it won't always look like this. All right. Okay, and then the last one, what if we dissolve exactly 90 grams of solid in 100 grams of water? What kind of solution is that? Ask yourself, when you make this solution, will it accept any more solid? No, it won't. So what kind of solution is it? Saturated. Yes, it is saturated. It will not accept any more solid. Perfect. Okay. Okay, so in these examples, these are things that you could do in lab or you do in the kitchen, right? Dissolve 5 of this, 10 of that, or 5 of this, 100 grams of water, different amounts, and you'll see unsaturated versus saturated solutions. So the question is, well, how do you make a supersaturated solution? Well, I mentioned it's actually very hard to make one because they're very unstable. So how do you make a supersaturated solution? You need to trick it. You need to trick the solution in order to make it supersaturated. But here's the thing, once you make that supersaturated solution, you can just yell at it and it'll, the supersaturated solution will fall back down to a saturated solution where solid will fall out. So here is how you make a supersaturated solution. Typically what you have to do is you make a highly concentrated solution, you make a saturated solution, you heat it up, and then you cool it back down very, very slowly. So let's look at this example. So let's take 100 grams of solid and 100 grams of water, and let's boil it to 100 degrees Celsius. So let's look at this graph and see where we are. So if we're at 100 degrees Celsius, we're like somewhere right here. All right, this is 100 degrees Celsius. And so we are going to dissolve, what, 100 grams and 100 grams of water. So we're right here on that graph. So what kind of solution is that? 100 grams and 100 grams of water at 100 degrees Celsius. That is unsaturated, yes. Okay, because at 100 degrees Celsius, you can add more solid before you hit that limit, that saturated line. Now what we're gonna do to make a super saturated solution is we're gonna cool it down very, very slowly. We're going to cool it all the way down to 30 degrees Celsius. We're going to cool it down so slowly that no solid, we're going to prevent solid from forming, from falling out of solution. So let's see at where 30 degrees is. 30 degrees was like right here. So we're going to cool it down very slowly and try to keep all 100 grams of that solid dissolved in the solution. So let's see what happens. If we cool it down very slowly, we're actually going to move horizontally across this graph. So once we get a little bit lower than 50 degrees Celsius, you see that we pass over that saturated line. And this is where you have to do it very slowly and trick that solution in keeping all 100 grams in this dissolved in the solution without crashing back out. So if we do that, and we're able to keep all 100 grams of that solid in solution, but maintain it at 30 degrees Celsius. Here, we've tricked the sample in keeping all of that solid dissolved in water. And now this is a supersaturated solution. All right, this is supersaturated. Just dissolving 100 grams of solid and 100 grams of water and mixing it for a long time will never make a supersaturated solution. It's going to stay saturated because that 10 grams of extra solid at the bottom has no way in getting dissolved into the solution. But the way to make it supersaturated is to trick it by heating it up and cooling it back down very, very, very slowly. So all 10 grams stay, or all 100 grams stay dissolved in solution. So in this case, cooling it back down makes it supersaturated. But once you have that supersaturated solution, just tapping it will make all of it fall out of solution. And here's an example of a supersaturated solution. These are, have you ever seen these reusable hot packs? Yeah. I've seen a lot of skiers use these. All right. So these reusable hot packs, all they are is filled with a very, very concentrated sodium acetate mixture. And so to make these reusable hot packs, what you have to do is boil that. Has anyone ever used them? No one? You have? Okay. All right. They're not super common. And I think it's because they're annoying to use. Okay. Because in order to reuse them, you have to boil them. You boil them for a long time. And what that does is makes a very, very, it gets all of that solid dissolved into these packs. And so in order to release the heat of these reusable packs, what's in here is like this little like coin that you like click. It like clicks. And once you click it, that like tiny bit of physical energy forces all of the crystallization to happen, to force that supersaturated solution to become a saturated solution. And in that same time, it releases a lot of heat. And so that releasing of heat is what brings it back down to just a regular, stable, saturated solution. But once it's saturated, then it's no use to us anymore. In order to reuse it, you have to boil it again to make it, to get all the solid to dissolve. It cools back down so it's super saturated. And then when you click it, it releases back down I guess, saturated zone here, and it goes back down to being a just regular saturated solution, and it releases heat at the same time. So there is an example of supersaturated solutions, but it's very, again, very difficult to make because in order to reuse these reusable hot packs, you have to boil them in order to make that supersaturated solution. Again, so you're probably not going to be making supersaturated solutions in lab. They're quite difficult to make because you have to heat them up and cool them back down very, very slowly. All right, so those are saturated examples. Okay, so let's put it all together and look at this graph and think about scenarios of saturated solutions and changes we can make, and think about how does making these changes to this mixture change the amount of solid that's at the bottom of the beaker? How does it change the concentration of the surrounding solution? How can we navigate differently on this solubility graph? So let's look at this example. So let's take solid. It doesn't really matter what it is. We add it to a beaker and we stir it for a very long time. After a while, we observe that most of the solid dissolves, but some of it remains at the bottom of the beaker. So at this point, what kind of solution is this? Unsaturated, saturated, what? This is saturated. Yeah, so we're sitting somewhere on this line. So what this solution looks like is something like this. A lot of the solid is dissolved, but you got a big chunk of it at the bottom. So we are looking at differences as, okay, how does the aqueous phase change and how does the solid phase change when we make these little adjustments? So what if we heat the solution? What's going to happen to the amount of solid that's present at the bottom? And how is the aqueous phase going to change? Use your intuition. Heating it will do what? You told me this at the very beginning of this section. Heating it will do what to the solid? Dissolve it. But where does the solid go? Does it just go away? No, it goes into the solution. So yes, heating the solution removes, I guess, lowers the amount of solid that's at the bottom of the beaker. But how does that change the concentration of the surrounding solution? It goes up. Yes, it goes up. The solid disappears, but it gets dissolved into the solution. So the concentration goes up. And so the reason that happens is heating it, we're actually moving somewhere else on this saturated line, right? That we're able to dissolve more of the substance because we're heating it up, we're moving horizontally across that line. All right, what if we allow some of the solution to evaporate? So when we allow the solution to evaporate, only water is being removed. So water is removed. Okay, so when we look at this graph, note how the line here is how much solid can dissolve in 100 grams of water. So if we remove some of the water, the amount of solid at the bottom of the beaker is going to go up. Because if you think about this, what amount of water can dissolve more stuff? 100 grams of water or 50 grams of water? Obviously, 100 grams of water is going to dissolve more stuff. So if we remove some of the water, we're not going to be able to dissolve all of that solid that we wanted to. So the amount of solid is actually going to go up. But how about the concentration of the stuff around it? It's not going to go down. It's actually going to stay the same. Yes, it's going to stay the same. No worries. So it's going to stay the same because we still, when we evaporate a little bit of water, all right, the solid falls out of solution. Some of that solid falls out of solution, but we haven't moved anywhere across the solubility graph. We're still at the same temperature. So we still have a saturated solution, whether you have 100 liters of saturated solution or 5 liters of saturated solution. The concentration is still the same. It's just the amount of solid at the bottom is different. For both examples. So the concentration actually stays the same. But in A, the concentration changed because the solubility changed. Solubility changed. Because your temperature changed. Okay. All right, so that one's tricky. So C, what if we remove some liquid off the top? So if we look at this example, if we remove some liquid, we have a saturated solution. And we just like remove this top layer. Boop, just scoop it up. Does it change the amount of solid that's at the bottom? Nope, no change. Yeah, so the solid has no change. Did you change the concentration of anything? Nope, no change. Correct, no change. Note how B and C, they sound similar, but they're different, all right? C is different because you're scooping the solution off the top. You're removing water, but you're also removing that solution, the solute particles that are already dissolved. B is different because we're letting it evaporate. We're only letting the water evaporate, but the solute particles are still there. When you have a like glass of salt water or like glass of water sitting on your nightstand and you let it all evaporate, after all of it evaporates, you see like little specks of white stuff at the bottom. Those are the minerals that are in your water, that you're drinking water. Those minerals are left behind because the only thing that evaporated was the water. So that's how B and C differ, that only the water evaporates, the minerals and the salts all stay behind. Right, cooling the solution. So cooling the solution, think this is actually very much related to example A. Cooling the solution, we're actually moving across this solubility graph, right? Typically, heating something up increases solubility, but decreasing temperature actually lowers solubility. So we see here, cooling the solution, it's going to have the opposite effect of heating it. So the amount of solid at the bottom actually increases. And then how does the concentration of the salt, the aqueous phase, change? It will decrease because your saturated solution concentration decreases. You're somewhere else on this graph. We started here, but now we're here. We could dissolve 90 grams, but now we can only dissolve 80 grams. And so that concentration will change. What if we add a little bit of water? Just a tiny bit of water. What's going to happen to the amount of solid at the bottom? It's going to go down. Yeah, adding a little bit of water will dissolve more solid. But here's the thing. I say that there's still solid present at the bottom. So what kind of solution is this still? It's still saturated. So did the concentration of the surrounding change? No change. Yeah, we did not move anywhere on that graph. So this is no change. What if we add a really large amount of water so all of the solid dissolves? So if all of the solid dissolves, obviously the amount of solid is going to decrease. But how does the concentration change? If we add so much water, everything dissolves. The concentration is actually going to go down because at this point you're adding so much water. This is actually called dilution. That's all you're doing. M1 V1 equals M2 V2. So once we have an unsaturated solution, unsaturated, this is just dilution. So you just do M1 V1 equals M2 V2, and we no longer have to think about that solubility graph that we were showing you earlier, right? So, in 1210, we mainly worked with unsaturated solutions. We dealt with M1 V1 equals M2 V2 all the time. But in this chapter, we're looking at the, subtleties of saturated solutions and how all of those things come together. Okay, so I got 5 minutes. Let's talk. Let me see what. Let's just review a little bit, and I'll give you Thursday to review intermolecular forces a little bit, because all of this comes together on how we make solutions. Especially when the energetics of solution making that we talked about earlier come together, intermolecular forces play a very, very big role. So it's best for you to review intermolecular forces and how you can determine what IMFs are present if I give you a certain sample, because now we're taking those intermolecular forces and we're mixing them with other things. So we'll look at factors that affect solubility. You can dissolve solids in water. You can dissolve liquids in water. You can also dissolve gases in water. And we'll look at all three of those examples. All right. How many of you took biology? Yeah, okay. So have you ever heard them say, or ever heard the phrase like dissolves like? Yeah, like polar things dissolve polar things. Non-polar things dissolve non-polar things. So that axiom is kind of right, but also a little bit wrong, or it's a little bit too simple. And so we'll look at the nitty-gritty details of that coming up. So these are the intermolecular forces you need to review from 1210. All right, so we'll stop at this slide. But the three main ones that we talked about in 1210 were dispersion or London dispersion forces. So the criteria for a sample for London dispersion is typically non-polar compounds. Those are the non-polar compounds only have dispersion forces present. On the other hand, we had dipole-dipole attractions. This was important in polar compounds. Polar compounds have permanent dipoles, so you can think of them as like little magnets that are attracted to each other, right? The last most, the strongest intermolecular force we talked about was hydrogen bonding. And so hydrogen bonding has a very specific criteria. It can't just be any hydrogen. It has to be a very electropositive hydrogen that's attached to either an oxygen, a nitrogen with a lone pair, or a fluorine with lone pairs. These are the only functional groups that can participate in hydrogen bonding, right? So for example, this compound, even though it has an H and it has an F, cannot do hydrogen bonding because the hydrogen has to actually be attached to the F. It can't just be any old hydrogen doing hydrogen bonding. It has to be one that's attached to a very electronegative atom. So this cannot do hydrogen bonding, but these three groups can. So keep that in mind. And then on Friday, we'll talk about this new intermolecular force ion dipole that's very important in talking about dissolving ionic substances. All right, so do review those things for Friday. So let's end this class with a bang. So for those of you new people who didn't take 1210 here, yeah, let's just do that. Okay. Tell me, I'm going to do this reaction, and after it's done, you're going to tell me what is the sign of delta H of this reaction. So use your observations. Tell me what is the sign of delta H of the reaction when I do this. Okay. Okay. All right. So this reaction is very loud. So I need everyone to cover their ears. Everybody cover their ears. What you can do instead of like putting them like in your ear, if you kind of do Dumbo ears backwards, you can like really, you can still feel it and hear it if you want to hear it. So, okay, headphones. All right, ears, everyone. So this will be a great fast year. We'll start with a bang and then we'll end with a bang at the end of the year as well. All right, let's have a good year. Okay, so what was the sign of delta H? Positive or negative? Negative, very good. Negative. Oh yeah, I have office hours right now if you want to come. Give me 1 second.